The assignment for today is 1.7, and this is all about inverses. Inverse functions. Inverse functions for, if in secondary math 3 last year, inverse functions was the third unit that you did last year. The order of ideas last year was 1, polynomials. This was last year for secondary math 3. If you took secondary math 3 last year, this is the order. It should have been polynomials first, followed by rational functions, rational, followed by inverses, and then followed by logarithms. That was for secondary math 3. So we are right now going to go over inverses. We've already talked about polynomials, we've already talked about rationals, and we've already talked about logarithms. Now we're going to be talking about inverses. Now, what's really cool about inverses is that, I mean, if you were to write an equation like 5 plus 3 equals 8, if you go from left to right, like you do reading a book, then we see that the operation is addition. 5 plus 3 equals 8. But if we go backward, now some people want to call this an opposite. It's not an opposite, it's an inverse. An inverse is, you're basically going backward. It's 8. In this case, it would be 8 minus 3 equals 5, right? Just going backward. If you are packing to go to a foreign country, I want to go to Madrid. And when I get to Madrid, it's going to be night. The first thing I want to be I'm just going to get to the hotel and I just want to crash. So I am going to, when I pack my suitcase, where do I want to put my pajamas? I'm going to pack it at first, middle, or last. I'm going to pack my pajamas last. That's an inverse. I pack it last so I can take it out first. Does that make sense? That's what an inverse is. It's basically going backward. We don't want to call it opposite because it's not quite an opposite. You're just basically going backward. So what's really cool about inverses, if I look at something like, we've talked about logarithms already, and all logarithms come from what? Why do we even have logarithms? They are inverses of what? Of exponential functions, right? We have an exponential function right here of, let's say this is y equals 2 to the power of x, which means this point right here is going to be what? Right on the y-intercept has to be what? What's that point? Well, it's a point with an x and a y. It has an x and a y value. What are they?
0 and 1.
0 and 1. Yep. So I know if this is, so 0, so this would be 0. This value here, oh, sorry. If I want to find a y-intercept, what has to be 0? For a y-intercept, what has to be 0? X. So we'll make this 0, and we get 1. The answer is 0, 1. That point here is 0, 1. So this point right here is 0, 1. Now for all inverses are reflections of each other across the what line?
Y equals X.
Y equals X. Good. Y equals X. That means that if X is 1, Y is 1. If X is 2, Y is 2. If X is 3, Y is 3. If X is 4, Y is 4. We have that line that's diagonal right across, diagonal through the first and the third quadrants. And so we have another graph that has to be the inverse. So we'll say that I'll just use orange. Not that that's that much different. This graph here, if it's a reflection across the y equals x, has to be what? Y equals what? How about log base 2 of x? So this point right here is what? What's this point?
1.0.
Yeah, it's 1, 0. For inverses, x, the x's become the y's become the x's. This is a really important idea when it comes to inverses. All inverses. Okay, I'll just write this out. Okay, properties of inverses. Properties of inverses. X's become y's and y's become x's. That's one of the important properties. They are also reflections of each other across the y equals x. Reflections across, sorry, how you spell cross, across y equals x. That's an important property of inverse functions. You could also say something about the domain. The domain of one function becomes what of the inverse? The range. So those reverse. I almost want to write that, but isn't that sort of implied here? Because the x's are the domain and the y's are the range. So when the x's become the y's become the x's, you are specifically talking about the domains and ranges switching. So I don't really feel like I need to write that. So I feel like those are just those two properties. I thought there was more properties. Yes, Brent. Oh, that's a very important property. Thank you. They cancel each other out. That's the point of inverses. They cancel each other out. That is a very important property of inverses. Can you think of any other? Can you think of any other ones, Brandon? I missed that. Okay, I missed that important one. Thank you. Thank you for keeping me honest. That is a very important one. We cancel each other out. All right. Now, if I come back, if I can think of another one, I'll come back to this. But I'm pretty sure that we're good there. I think we're good there. All right. Let's say that I have something. Oh, let's talk about this idea of one-to-one. What the heck is this idea of 1 to 1? Now we know what a function is. With a function, for every x value, how many y values do we have assigned to them? One. When we talk about something one-to-one, it also has to be true going the other way. For every y value, there's how many x values? There's only one. That's for a one-to-one relationship. If it's one-to-one, and the point of a one-to-one is that the inverse is also a function. The point of identifying something as one-to-one means that, in fact, I'll spell this out first. For every x value, there is no more than one y value assigned to it. No corresponding y value. There's no more than one corresponding y value. That's how we define a function. Do you agree, Adam, that that's how we define a function? For every x value, how many y values do we have? There's just one. Now, when we have something that is considered one-to-one, then we go the same way the other way. For every y value, there. Brendan, is this getting too sloppy? And I want you to. I want you to be critical. If you can't read it, then please be critical. For every y value, there's no more than one corresponding x value. So what this means then is that the inverse is also a function. In fact, we have a vertical line test to test this. We have what's called a vertical line test to make sure that for every x value, there's no more than one y value assigned to it. We have what's called the vertical line test for this. Any guesses what the test is for this? Yeah, there's a horizontal line test. A horizontal line test tells you whether the inverse is also going to be a function. So here's an example. Here's an example. I have this graph right here. Is this a function?
Yes.
Yeah, this is approximately, this is like y equals x squared, right? It's a quadratic. This is a function. We can do a vertical line test anywhere to see that we cross no more than one time. For every x value, there's no more than one y value assigned to it. All right, is it one-to-one?
No.
No. How can we test to see if it's one-to-one? Horizontal line test. Now it has to pass, it actually has to pass both. It has to pass a vertical line test and a horizontal line test. In order to be one-to-one, we have to do both. We know that it passes the vertical line test. It is a function. Does it pass the horizontal line test?
No.
No. If I do a horizontal line, I pass the graph more than twice, which means that for y values, for some y values, I have more than one x value assigned to it. So in order to be one-to-one, it has to pass the vertical line test and the horizontal line test. In order to be one-to-one, the graph must pass the vertical line test and the horizontal line test. So I'm going to do what about this? Is it a function?
Yes.
I agree with you. It's a function. It's not going to violate the vertical line test. Is it one-to-one?
Yes.
It's also one-to-one. It passes both. I can do a vertical line test. I only pass any given point once. I can also, on the graph, I can also do a horizontal line test and also see that any horizontal line only passes the graph no more than one time. So this is a one-to-one. This function is a one-to-one, which means what about its inverse? Okay, it exists. The inverse is also a function. It means so if I do what does the inverse for this look like? It has to be a reflection across what line? Yeah, so we have this line like here. Oh, actually, I think I missed the line. It's here. So we have a graph that looks like something like this, which is certainly not a function. And this one here, I have to reflect across this line right here. So it'd look, this is going to be hard for me. That one's going to be hard for me. It's going to look something like that. Anyway, the point is it's going to still be a function because it's one-to-one. Jacob, where's Jacob? What does one-to-one mean? What does one-to-one mean? It has only one corresponding y value, yeah. But it also means that for every y value, yeah, so it's both, right? If it's just the one, there's another name that goes with it. It starts with an F. If it's just the one where every x value only has one corresponding y value, there's another name for it. It starts with an F, as in Frank. if for every X value, there's only one corresponding Y value. It's a function. It's a function. It's a function. And then if it's both, then we call it one-to-one, if it's both. Okay, so let's do an inverse. So here's an example. So I want to find the inverse. Find the inverse of f of x equals 3x plus 5. Do you want some think time, or are you already lost? This is something you should have learned last year in secondary math 3 on inverses. If you're already lost, I don't want to spend class time for you to just look at it and not do anything. Do you want some think time, or are you already lost? Think time? Thomas, are you already lost?
No, I already did it.
You already did it?
Yeah.
Crazy. Thomas, what did you do?
Well, first I put f of x for x and x for x.
Okay, so you just changed the variables, right?
Yeah.
Isn't that one of the characters of an inverse? When we go up here, one of the characters is what?
Yeah. So x is y, y become x.
Yeah, the x's become the y's and the y's become the x's. Okay, and so so we just reverse the variables.
Yeah. And solve for y.
And then we just solve for y. So the steps are to find an inverse, switch the variables. Ah, my word. The variables, and then solve for y. Yeah, just really just 2 steps. If you want to be fancy, the last step would be use function notation. Use function notation. And I'm going to do the last step because I know I'm spelling notation. No, notation. There we go. Notation. I'm going to do the last step because I want you to be able to recognize when you see something, I want you to be able to recognize it as an inverse when you see it. Okay, so let's pick on, that's Kian. Where's Kian? Kian's not here? Okay. Where's Nathan? Nate. How do I solve for this? If I'm solving for y, how do I do it? What are my steps?
Subtract 5.
Okay, subtract 5, so I get x minus 5 equals 3y, okay? And then divide by 3, so I'm going to get something like this, y equals x minus 5 over 3, right? Okay, now I'm going to use this function notation to indicate what this means. I'm going to translate this into the inverse. And if this function right here is our f of x function, then my inverse is written like this. Now, don't get this confused for an exponent. This is not an exponent. This is read the inverse of f of x. Think of it as there are some things that have multiple meanings in English, right? If I talk about right, what am I talking about if I use the word right?
The correct, you're going to that direction.
Yeah, we're talking. Yeah, you could talk about direction as one type of right. We can also talk about whether you're correct or not, right? There are 2 different ways of what it's 2 different meanings, or I think there's multiple meanings for right, but that's my point of this what is it called? A hyperscript. A hyperscript. That hyperscript has more than one meaning. The hyperscript means the inverse. So that's how we write it. Now, if I graph this f of x and I graph the inverse of f of x, then what relationship are they going to have on the grid? They're going to be reflections of each other across the y equals x. Yep, they will be reflections of each other across the y equals x. In fact, I don't just little bit nervous about time, but I think it's still worth looking at. So let's go to Desmos. Let's see if I can do this fast. And then our first graph, we have f of x equals 3x plus 5. And our inverse is this x minus 5 over 3. And are these reflections across the y equals x? What do you think? How does that look? Do they look like reflections?
Yeah.
Yeah, so we did them right. Is my function a one-to-one?
Yes.
Yep. And we can verify that even by looking at our graph, our inverse. Our inverse is also a function. So it had to be one-to-one. Okay. This is the next one. I want to find. Am I going too fast? Good speed. Okay. I want to find how do you read this? Bryn, how do you read that? How do you read this?
Find the inverse of fx for fx equals 3, or x cubed.
Yeah, perfect. Yeah. Find the inverse of f of x if f of x equals x cubed. Nice. Okay. Where's Maya? Maya, are you done? Okay, what did you get? The inverse of f of x equals what? Yeah, with plus or minus? Do we need that? Why not? Yeah, well, what about if it's the fourth root? So what's the rule? Perfect. If it's even, then you need it. If it's odd, you don't. So we're not going to worry about plus or minus. So you were correct. You never said plus or minus, but I just wanted to test you because some students are unsure. So we're just dealing with this, the cubed root of x. Do you think these are inverses, or do you think x cubed is a one-to-one or no?
Yes.
Yeah, I agree with you. If I had a plus or minus, that would be suspicious that maybe they're not inverses. So we could test this and see. Let's go back to this graph here. We have our f of x is x cubed, and our inverse is our, I think I'm going to have to go y equals, I think I'm going to have to go here. I'm not sure what these, yeah, miscellaneous. Yeah, a lot of times I know the hotkeys for it, but I don't know this one. So there we go. So the third cube, there we go. And there we go. These should be reflections of each other across what? Y equals x. How did we do? Yeah, we did good. Okay. All right, let's do another one. Find what does this say? What does this say right here? The inverse of g of x. Do not get this confused as an exponent, because we're going to see something like this later. What does this mean? What does this mean here? What is it? The inverse of sine. It's the inverse of sine, or we also can call it arc sine. Have you heard that before? This is the inverse of sine, or we can call it arc sine. Both of them are correct. Okay, so this means the inverse of g of x. So I want to find the inverse of g of x. Bentley, we'll do that again later today in class. So if you're writing that down, sorry. Okay. The inverse of g of x for g of x equals 2x plus 4 over x minus 1. I want to give you some think time, but not a lot. I'll give you a whole minute of think time. I'm that generous. Gaia, where did you start? So what is this? If I have to turn things in from x to y's and y's to x, what is this to begin with? What is it? It's a y. Yeah, it's a y. So I'm going to change that to an x, and then the x is to y's. Okay, I like it. I like it. Where's Ethan? Oh, yes.
You forgot to do the bottom x to the y.
Oh, thank you. That would have messed me up. I will. Yeah, please keep me honest, because all it's going to do is just, I'm going to do this whole mess, and then we have to go back and do it later the right way. So let's make sure that we do this right to begin with. Ethan, what did you do next? What's the second step? What was the second step? Where is the second step? Oh, here's my steps. What's the second step? It's pretty easy. It's just switch and then solve. How do I solve for y? How? Can I go like this?
No, no.
Why not? Because these are not factors. You can't eliminate it because they're not factors. That would be, so if I have factors like this, I can certainly eliminate those and I get 3. That would be silly to say 15 divided by 5 is 10 plus 5 over 5. Eliminate those and the answer is 10. That's just silly. That's just silly math. So of course we can't do it that way. So we can eliminate. I'm not accusing you, Ethan, of doing that, but Ethan, I do see other students do that, and so I just get concerned. So how in the world would I do this? Evan, any ideas? Well, so we put negative what in the denominator? What's in the denominator? Now we're not going to, we'll never multiply by anything except for 1, right? We have to multiply by 1. If we multiply, say by, I don't know, 4 or something like that, we've just changed the quantity. So we have to multiply by 1. So you could do, this is fair, you could do that, but I don't think that helps. I don't think that helps to do that. Thomas, question. Help me out. Yes.
All right, first thing you gotta do is multiply y minus one both sides. So you can't do one.
Wait, multiply by what?
X minus one.
X minus 1. Nice, because we're,
Y.
in-
Y.
in fact, what I want to do, if you can't think of where to start with something. If you can't think where to start with something. Even if you think it's going to be a dead end. A lot of times, in fact, a lot of mathematicians have discovered things by thinking it's a dead end, but they explore it anyway. I don't know what to do. So at least let's at least make sure it's not a fraction anymore. Yes, sir.
It's y minus one to both sides.
Correct.
Both.
Correct. I do apologize. So what you're actually not multiplying by 1, right? You're actually multiplying. In fact, you said it right. I just wrote it down wrong. So you're going to multiply by y minus 1. If we do that to both sides, that's fair. That's a balance. It's our equation then is balanced. So that's fair game because of the the laws of equality would make that true. Now, by doing that, that allows us to eliminate this over here. But what do we do over here?
Well, we factor.
Okay, how about if we do the opposite of factor, which is especially the distribute. Yeah. So we're going to distribute, and if we distribute, we get what?
Xy minus x.
Xy minus x. Now, even if you think it's a dead end, we don't know what else to do, so let's just explore this anyway. What do we still have over here?
2y plus 4.
We still have a 2y plus 4. Now, I'm getting a little crowded over here, so I'm just going to bring this down so that I just don't want students to get things mixed up for what still belongs in what. Is everybody following? Am I going too fast? Is Thomas going too fast? Okay, and I make sure that I'm being honest with how I write things so that everybody follows. Math should make sense. Math should make logical sense. Now remember our goal. What is our goal? What are we trying to do? We're trying to get y by itself. Now, I don't have all the y's on one side even. So what do you think the next step might be?
Well, to isolate the y. That's y.
Yeah, anything that's y, bring it over here. Anything that's not y, move over here. Does that make sense?
Yes.
Okay, so I'm going to do what then?
You're going to add x to both sides.
We're going to add x to both sides. So that gives me 4 plus x on one side.
Yes. And you're going to subtract 2y.
Okay, that gives me xy minus 2y.
Yes.
Does that look right to you guys? Okay, now what?
Now you would factor out the y.
Now we can factor out the y. Now if I factor out the y, that's going to give me y times the quantity of what?
X minus 2.
X minus 2 equals 4 plus x. How does that help?
It allows us to isolate the y.
Yeah, so what's my next step?
X minus 2 to both sides.
X minus 2 to both sides, x minus 2. This goes away, and I'm left with y equals 4 plus x over x minus 2.
And now you
Yeah, now we can do function notation, or inverse notation. So that'd be the inverse, was it f of x or g of x?
see that.
Okay, so this would be the inverse of g of x. Inverse of g of x equals 4 plus x over x minus 2. Bryn, is that what you got? So what did we do? If you have a problem like this, step me through how to do this. Bentley, step me through how to do this. If I have g of x and I have this ugly fraction to deal with, step me through how to do this. What did we do? What was our next step? Our first step is what?
To switch the variable.
To switch the variables. So we changed all the x's to y's and all the y's to x. What was the next step?
Next up was to solve y.
Okay, how do we solve for y?
First, we multiply the bottom by y, or we multiply one side by both sides by y minus 1.
Yeah, we multiplied both sides by the denominator to get rid of the denominator. Even if you have no idea where to go, at least do something as a first step. You might discover something that you didn't know that you could even do. Okay, so we multiply both sides by y minus 1, which eliminates the denominator altogether. Okay, Bentley, now what?
That gives us x, y minus x, or
Well, how did we get this?
you distribute to get x, y minus x is equal to 2y plus 4.
Okay.
And you trying to get y by itself, so you end up adding
So-
negative, you end up adding x to both sides and minusing 2y to both sides.
Because you want all of the terms with y on one side, all the terms with not y on the other side.
Yeah.
Right, okay.
Which gets you xy minus 2y equals 4x, 4 plus x. You then factor y out of xy minus 2y to get y times x minus 2, which is equal to 4 plus x. You then divide both sides by x minus 2. It cancels out on one side, you get y, on the other side, it gives you 4 plus x over x minus 2.
Nice. Do you need some time to copy this?
I just finished.
Yeah, awesome, cool. Okay, you will have a question like this on your test. So make sure you know how to do this. Adam, are you comfortable with doing it this way? The inverse. Okay, let's make sure that there's no confusion. So Adam, what was the first step? Here is my original equation. I want to find the inverse. So what's the first step? Yep, switch the x and y's. What was the next step? Well, how did I cancel out the denominator? Yeah, multiply both sides by the denominator. Now what did I do? How did I go from here to here? I distributed and then anything that has a y needs to be on this side. Anything that doesn't have a y needs to be on this side. Okay. And then once we have all of our y's on one side, anything that doesn't have y's is on the other side. What do we do? How do we move from here to here? Adam. Starts with an F. We have to factor. We factor out a y. That leaves us y times the quantity of x minus 2 on one side. Now what do we do, Adam? Correct. That is perfect. Now, if I graph these inverses, what should we see?
They reflect off the line.
Yeah. What kind of functions are these? What function family does this belong to? Starts with an R. Louder. It's rational. It belongs to the rational function family because any rational is a polynomial divided by a polynomial. That's what we see here. We have a polynomial divided by a polynomial. So these should be rationals, which means that an important characteristic of rationals is asymptotes. So there should be a bunch of asymptotes here. So I have y equals, and then we have 2x plus 4 in the numerator and x minus 1. There's 1. And we should have a reflection across the y equals x for our other function of here. We have y equals 4x plus 4, oh, plus x, sorry, x over
Isn't it just 4
x
plus x?
minus 2. 4, oh, just 4, sorry.
Yeah.
Is that better? Yeah. So the question is, are these reflections of each other across the y equals x?
Yes.
Yes.
Yeah. So we know we did it right. They're reflections of each other across the y equals x. Okay. Now we're going to do inverse trig. Inverse trig. I'll just go to the top again. Let's zoom in. And Bentley, yes, question. Okay. My only concern is the steps should still be the same. And I am a little bit concerned about time is all, because we are going to get through a lot of stuff. But the steps should still be the same. We reverse the variables. And then for a fraction like this, we reverse the variables and then get rid of the denominator by multiplying both sides by the denominator. Natalie, if you have a specific question that you're struggling with, email me. You can say, this feels different, Mr. Hall. Natalie, are you okay? Are you okay? Okay. Yeah, just email me. Take a screenshot and send it to me and say, Mr. Hall, this doesn't, just show me your work, and then I'll show you the next step. Okay. That goes with all of you. You're certainly welcome to do that. Okay. I just get really frustrated when I have students that say, I don't know how to do this. Well, show me, can you do something? Show me some steps or some thinking that's going on. That's usually more helpful. All right, so we're doing inverse. I think I was going to go over to the other side. We're going to do inverse trig. Inverse trig. So I have sine of theta equals the opposite over the hypotenuse. So remember that this sine is just a definition. Oh, and Natalie, another option too, if anything, is remember, I'm not going to spend class time per se doing any questions, but if you do have a question, just tell me at the beginning of class. Say, Mr. Hall, I really didn't understand this one. Can we do it as a class? And I'll be glad to do that. Okay. So I certainly do feel that, you know, when I was taking math classes, Natalie, it did feel sometimes that you go to the homework and it feel different. And it does, the homework is there to as a tool to get repetition, but it's also there for as a tool to give you variation as well. So it challenges you in different ways. So, but yeah, if something's too confusing, either reach out to me via email or bring it to class and say, yeah, this seemed too different. So what if I wanted, so this is just the definition of sine is just a ratio, and it means opposite over hypotenuse. And so you have some, I don't know, some triangle here, and we'll say that this is our theta, and this is our opposite. We'll say this is, say, I don't know, 1, and this is 2 right here. Then how would you find theta? How could I isolate theta? That's a pretty important question with trigonometry. How do you isolate theta? Finley.
Wouldn't you use arc sine?
Yep. Use arc sine or inverse of sine, either way is fine with me. So you're going to rewrite this as, in fact, if you prefer, you can even rewrite this as the inverse of sine, which are inverses and they undo each other, and you do the same thing on the other side like this. Now, what that gives you then, since those are inverses and they undo each other, we're left with theta equals the inverse of sine of the opposite over the hypotenuse. That will give us, the inverse gives us the angle. Because the inverse gives us the angle, we need to make sure that our calculator is in the right mode. And in AP calculus, 99, actually I can't think of any time that you're going to be dealing with degrees. It should always be radians. So you're going to be using, make sure your mode is in radians. So what about cosine? Cosine of theta. Cosine of theta is adjacent over hypotenuse. How do I isolate theta here? Yeah, we can do the inverse of cosine. So we do the inverse of cosine. The inverse of cosine of our adjacent over hypotenuse. The point of an inverse trig is to find what? The point of an inverse trig is to find what? To find the angle. Yep. The whole point is to find the angle. And I do want to mention that this means this is read the inverse of sine, or you can say arc sine. It means the same thing. Kyler, how are you feeling? Awesome. Cool. Okay. Let's do a tangent. Tangent of theta. Tangent of theta is, by definition, tangent of theta is what? Yeah, it's opposite over our adjacent. It's just a ratio. Opposite over adjacent, because for any angle, that ratio is going to be the same, whether it's a little triangle on Earth or whether it stretches out all the way across the universe. And we have some triangle out in space to find the distance of some distant star. That doesn't look like a triangle very well. Yeah, I was wondered in high school, how do we know? Alpha Centauri is 4 light years away. It takes 4 years for light from Alpha Centauri to make it to our eyeball. How do we know that if we could never travel that far? It's trigonometry. Trigonometry. The triangle on Earth is similar to a triangle that stretches out into space. As long as those angles are the same, then we have the ratio will be the same. So how do I isolate theta? Yeah, we do the inverse of tangent of both sides. The inverse of tangent of both sides. The point of an inverse of trig is to find what? The angle. The point of an inverse in trig is to find an angle. That's a very, very important idea. What if I wanted to find, let's go back here. What if I wanted to find, I don't want to spend a lot of time going over this, but we should be able to remember, what if I wanted to find theta in this case? Oh, well, what is secant? Yeah, this is 1 over cosine of theta, which means that this is going to be, what's my ratio then? What's the ratio? Yes, the hypotenuse over adjacent. So if I wanted to find theta, this is going to be theta equals the inverse of secant of hypotenuse over adjacent. Now, what if your calculator doesn't have secant, cosecant? I have a calculator. This is one of my favorite calculators. This is a TI-84. Does anybody have a TI-84? Do you have secant in your calculator? No, you don't. So how would I do this problem using my calculator? Yeah, just 1 over the inverse of cosine of whatever, of our adjacent over our hypotenuse, right? Yeah, we just do that. If you're using a TI-84, the TI Inspire has secant, cosecant, and cotangent. But if you have a TI-84, you're going to have to use this method here. This is actually my favorite calculator. I actually prefer this over the TI Inspire. But yeah, it does have its own limitations. Okay, can we move on? Bless you. Okay, I want to find I'm gonna zoom in. My handwriting actually gets better when it's a little bit thicker. So find the exact values. Okay, I have 4 problems. Give a little bit of think time. Adam, do you have the first one? Do you remember the hand trick? Okay, well, let's do the hand trick. I have this. And this is our, Adam, this is the first quadrant, right? So if the first quadrant we're rotating counterclockwise for positive angles, this is 0 or 0. What's this in radians? What's this angle in radians? Pi 6. What's this one? Pi 4ths. Oops, I should have done that after. What's this one? Pi 3rds. What's this one right here? Pi halves. Now, if I want to figure out sine, do I go from the pinky or the thumb? If I want to figure out sine, I go from the pinky. That's my sine. If I want to figure out cosine, I go the other direction. So I want to figure out the inverse of sine. The inverse of sine of the square root of 3 over 2. What am I trying to figure out? All inverses, all inverse trigs. What am I trying to figure out? The angle. This is what I want to figure out. This. How do I recreate that? What finger do I need to put down to recreate this? What's the equation that goes in the palm of your hand? Square root of x over 2. Yep. So what finger am I going to put down so that I can recreate this? The index. I'm going to put this finger down, which means the answer, because that gives me 3 fingers here. That's the square root of 3 over 2. So that means my angle is what? Pi 3rds. Yep, it's pi 3rds. That's pi. The answer is pi 3rds. Yep. The other way to figure this out is to draw. This is one of our special angles. This is one of our special angles. What special angle do you, so there's 2 special angles, right? We have a 45, 45, 90 or a 30, 60, 90 triangle. What do you think? Well, let's look at if 45, 45, 90 triangle means that the sides are the 2 sides are the same length, right? So this is, because this is our unit circle, this is 1, and you can go through all of the steps to try to figure out what that missing side is. What did we figure that was? What did we figure out x was when we did this? Yeah, we got the square root of 2 over 2. So I'm not going to go through all that again. We end up getting the square root of 2 square root of 2 over 2 for both of these. Now, if it's if our angle is 45 degrees or pi 4ths, right? Or pi 4ths. So we also have another triangle. This is our 30, 60, 90 triangle. And in radians, what's a 30, 60, 90 triangle?
Pi 3rds, pi 6. pi x triangle.
pi 30 is pi, sorry, I should have done that the other way, right? This is a smaller angle here. Pi 6, pi thirds, and this is our pi, this would be our pi halves. So I don't really need that. Now this is a unit circle. This is on the unit circle, so this is a radius of 1. And the relationship between, in all 30, 60, 90 triangles, for all 30, 60, 90 triangles, what's the relationship between the longest side and the shortest side? Longest side is what?
Yeah,
Compared to the shortest side? Yeah, it's half. The shortest side is half. Shortest side is half, so this is half. So we could figure out this missing side here by going through this whole process of the Pythagorean theorem again. And to find that the missing side then is how much? Oops. What did we get? We get the square root of 3 over 2. So we get the square root of 3 over 2. So that means then if I'm standing here and I'm trying to figure out what a, actually in this case, I'm standing here because that's my angle. So I'm standing from this point, this is me, not here. So from that point there where I have sine of theta equals, well, we know what theta is, right? Sine of pi thirds equals what? Square root of 3 over 2 over 1, right? Square root of 3 over 2 over 1. Square root of 3 over 2 over 1 or that. So that's the other method. What's your name? Yeah. Kidda. Okay, Kidda, that's the other way to do it. Is that you actually could write it all out. The third way to do it is to memorize the unit circle. That'd be the third way to do it. I think the hand trick is easier, in my opinion. Okay, yeah, that's fine. If you already memorized the unit circle, go that way. I don't have the unit circle memorized. I still use the hand trick. I have a master's degree in math and I still use the hand trick. I think this is a super easy way to just condense all of the entire unit circle. All right, let's go ahead and go look back at this here. How do we do what? So we're doing inverses. For all inverse trig, we're trying to find what? The angle. So there's some angle here. What is the angle? So what finger do I put down so that I can create 0 here? The square root is 0 over 2. We have to put this finger down, right? So that I have 0 fingers from this side. Don't I want 0 fingers from this side? So this would be the square root of 0 over 2, which is 0. And that finger is what? It's pi over 2. Yes, it's pi over 2. Pi. The angle is pi halves. Question. All right, this one's a little bit more tricky. What quadrant am I going to be in if tangent is negative? I'm going to be either in the second or the fourth quadrant. So let's assume, I guess there's two different, actually, how many answers are there? Does anybody know how many answers there really are here? There are infinite. Yeah, because we can keep on going around and around the circle as many times as we want. I mean, literally, for example, pi thirds. Where's pi thirds? Pi thirds is here. So we have, I guess this is pretty important. So I'm going to spend some time doing this. This was it pi thirds? Pi thirds. So this is pi thirds. This is pi thirds. Because we're dealing with sine, this is how much here of a rotation? That's 2 pi thirds. So sine of pi thirds gives us the square root of 3 over 2. Sine of 2 pi thirds also gives us the square root of 3 over 2. But if I rotate all the way around here, how many is that? Sine of 7. Yeah, let's divide it up. So we have this. There we go. 1 pi thirds, 2 pi thirds, 3 pi thirds, 4 pi thirds, 5 pi thirds, 6 pi thirds, 7 pi thirds. So sine of 7 pi thirds is also the square root of 3 over 2. So we literally have infinite answers. If we're looking for an angle, we literally have infinite answers. Now your calculator, what your calculator is going to calculate is whatever the easiest rotation is, whatever the closest rotation is. And if there's two rotations, like for example, cosine of, I don't know, pi fourths equals the square root of 2 over 2. Cosine has the same rotation here and here for this, isn't this point here for x, the square root of 2 over 2, for x, the square root of 2 over 2. And so which one are we trying to calculate? The shortest rotation, but they're the same. So the shortest positive rotation. That's the rule. You go with the shortest positive rotation. That's what your calculator calculates. So in my calculator, the shortest rotation or the shortest positive rotation, in this case, where is tangent negative? What quadrants?
7 and 4.
Let me move this down. I feel like I'm getting crowded over here. I feel like I'm getting a little crowded. And then I have students that email me and say, Mr. Roll, I was understanding everything until you started writing over everything, and then I didn't understand anything. So I want to make sure that I don't get that criticism. Although I think maybe it would be fair to criticize me already for doing that. All right, so for tangent, we have tangent is negative in the second and the fourth quadrant. So we're going with we always start at the positive x-axis. We always start at the positive x-axis. Where's the shortest rotation? Clockwise or counterclockwise?
Clockwise.
We're going to go clockwise. So we're trying to figure out what this rotation here is. But that means because tangent of theta is sine of theta over cosine of theta, it means if we're going to get 1, it means sine of theta and cosine theta have to be the same. What angle will give you the same for sine and cosine? Yeah, pi over 4. Pi over 4. So pi over 4. So is that my answer? Pi fourths? No. What is it? Negative pi fourths. Why is it negative pi fourths? Because we're going clockwise. Whenever you do a clockwise rotation, it is a negative angle. That is the answer your calculator is going to give you. Well, it depends on what the question is. It depends on what the question is. Well, specifically, if this was all the question was, is this. I would, yeah, it depends on what the question is. I would probably give it to you, but I don't think I left that one as a choice. Yeah, you really should do, the general rule is you rotate the closest rotation, or if there's two choices that are closest rotations, then you go with the positive one. All right, what about this one? What's this one right here? These are inverses, they undo each other. The answer is 3 pi fourths.
Yeah.
Is everybody all right with that? 3 pi fourths? What if you're wrong? What if this is not the answer? What was the rule?
You start from the positive x-axis.
Okay, so Bryn, what's the rule? Shortest distance. And if there's two that are the same distance? Okay, what is this? Using your hand trick, what is this? What is this piece right here? Square root of 2 over 2. Agreed? Because let's do this. Let's draw this out. Let's draw this out. So we are cutting this up into 4 slices. We have this. How much is this?
Pi.
It's pi. We're dividing up pi into how many slices?
4.
4. 1 because of this 4. Slicing. We have 4 slices. 1, 2, 3, 4. How many slices are we rotating through? 3. 1, 2, 3. We're rotating over here. So we're actually looking at this triangle over here. And it actually is similar to the triangle over here. In fact, it's congruent. It's congruent to this triangle over here. So we know we could actually figure out what this point right here is for our, is sine our X or our Y value?
Why?
Oh, value is going to be the same on this side as this side, right?
Yeah.
So what's the Y value here? Yeah, we can use our hand trick for sine of pi fourths, and we get the square root of 2 over 2. Now, because that Y value, it's our up down value, it's the same as this up down value over here. Is this Y value positive or negative? It's positive. So we have the square root of 2 over here as well. So the answer for all of this is what, Bryn? Is it the same as this? Why? Why is, Bryn, why is sine of pi fourths the same as sine of 3 pi fourths? Because in the first and second quadrant, sine is positive and sine is your Y value. So they're the same thing. So that means then, Bryn, that all of this is what? Which is what? Square root of 2 over 2. Yeah, the square root of 2 over 2. So I know it's the square root of 2 over 2. So I'm going to write this down as the inverse of sine of the square root of 2 over 2. Is that the same? Bryn? Is this the same? Yeah, they're the same. All right, so let's figure out what so let's go back to our hand trick. Well, first of all, Bryn, if anytime I use the inverse of a trig, what am I trying to find? The angle. I'm trying to find an angle. So what finger would I put down with the hand trick so that I can recreate the square root of 2 over 2 for sine? Okay, right here.
Yeah.
So what's the angle?
Pi fourths.
So what's the answer to this? Yeah. Yeah, the answer is pi fourths. Is that confusing? Bryn, how do you feel about that?
It's fine.
What about this one? What if I have cosine? Let's do the same one. Inverse of, is that what we did? Inverse of cosine of 3 pi fourths. It would be, this is the answer? Sure?
Wait, actually, it would be because that would be closest.
Positive.
Positive.
Yeah. Okay, the cosine, is that my X or my Y value? It's my X value. This rotation here of pi fourths is the same. It gives me the same X value or X distance as this 3 pi fourths. The X distance, this X value is the same except it's negative. So this point here, this X value is going to be what? What's the X value over here? What is it? It's the square root of 2. Is that too sloppy?
I think it's just too small.
The square root of 2 over 2. So over here, this has to be what?
Negative square root of 2.
Okay, so that's negative the square root of 2 over 2. This will be negative the square root of 2 over 2. So what I have, if I want to replace all of this, this is replaced by what? Negative the square root of 2 over 2. So that gives me the inverse of cosine of negative the square root of 2 over 2. So where is negative the square root of 2 over 2 for our x value? There's two locations. What quadrants is cosine negative? Second and third. So we also have an x value down here of the negative the square root of 2 over 2. So which one is the closest rotation? They're the same. From here, they're the same. So we go with what? The positive rotation. So the positive rotation would be how much of a rotation? 3 pi 4. So all of this becomes 3 pi fourths. That all becomes 3 pi fourths. Yes, sir.
I'm guessing the same type of thing would happen if it was like a sine value going from here to here.
So if you give me an example. So if I have sine, you want to use sine or cosine or what?
Yeah, sine. So my instead, so it's I don't know how to do that, but so for their second example of cosine, the inverse of cosine.
Oh, wait. Okay.
for your
The
previous
inverse,
example,
the inverse of cosine,
well,
or you want me to go back?
so for that one, is it basically just value inside both of the cosines? So the 3 square root of 4 stays the same because it's like, because the cosine is going into the negatives.
Because you're going into, well, if we went into the positive, it's the same way. If I do inverse of cosine of cosine of the square root, oh, I'm sorry, of pi fourths, it's just going to be more logical why you're going to choose this rotation here, which would be the square root of 2 over 2, compared to this rotation here, which is also going to be what for my x value? Square root of 2 over 2. It's more logical that you're going to go here, right? They're the same distance, but you're going with the positive rotation if they're tied for the same distance rotation. Here, again, we're tied. We always start at the positive x-axis. We're tied with this rotation compared to this rotation. The distance is the same, so we go with the positive rotation. So that's what your calculator is going to show, and that's what if they give you a problem like this, like on the AP test, that's what they want you to do. They want you to calculate one angle, and in this case, that angle is going to be, in this case, it's just pi fourths. Okay. All right, let's do this one. Let's do cosine of inverse of tangent. Are we running out of time? Of the square root of, oh, let's just do one. Let's do -1. Let's do -1. Let's see how painful that becomes. No, I'm gonna do the square root of 3. Okay, that's my final offer. Because of lack of time, we need to do something with this piece right here. Remember that tangent of theta is sine of theta over cosine of theta. What finger would we put down to get the square root of 3? You know? What finger, so we're looking at the square root of 3, right? What finger do we put down so that we would get the sine of theta over cosine of theta, and they would cancel each other out, and we're left with the square root of 3. What finger would we have to put down to make that happen? Where are we? The index finger? So that would be this. So we still have sine We have sine over cosine of our angle. And we have, so the index finger would be the square root of 3. The square root of 3 over 2 over 1/2. When we divide by fractions, here's a tip, keep, change, flip. So what's the angle? What's the angle? It's pi thirds. Wait for it. It's pi thirds, but it's negative. It's pi thirds. So we're dealing with pi thirds, but it's negative. Where is tangent negative?
Fourth quadrant and
The fourth quadrant and the second quadrant. So we're looking at here or here. What is the closest rotation?
fourth quadrant.
The fourth quadrant. So we're actually looking at this rotation right here. So that's going to be what? What is that rotation?
Pi thirds.
That rotation is negative pi thirds because we are rotating clockwise. So all of this is what? Negative pi thirds. So I get cosine of negative pi thirds. Well, what is cosine of negative pi thirds?
1/2.
Yeah, it's the x value right here at this point. The x value is going to be, is it 1/2 or negative 1/2? Is sine, which is your x, positive or negative in the fourth quadrant?
Positive.
It's positive, so that's going to give us 1/2. What finger did you put down to get 1/2? You put down, this is 0, 30 degrees, 45, 60. This is pi thirds of 60 degrees. From our cosine direction, we have 1/2. We get 1/2. A lot of stuff that we've covered. There's a bunch of identities that we need to cover, but you know what? The most important identities for this class, the most important trig identities for this class, the most important trig identities are, here's one. Does anyone know what this one's called? Oops. Let's change this as well. It's called the Pythagorean identity. For our unit circle. If x is your sine, x is your cosine and your y is your sine, this is your x and your y, then this is my unit circle, then I have x squared plus y squared equals 1. But if x is your cosine and y is your sine, then don't you get this? This is called the Pythagorean identity. This is you will see this on the AP test. Expect to see that on the AP test. This is something you have to have memorized. The other important one that we have is when we have tangent of theta. Tangent of theta has to be, it's in terms of sine and cosine. Sine over cosine. That's something you also need to know. You also need to know your reciprocal identities. You need to know that secant of theta equals what? 1 over cosine of theta. You need to know cosecant of theta. Cosecant of theta is what? 1 over sine of theta. These are called the reciprocal identities. We have the trigonometric identity. We have the quotient identity. We have the reciprocal identities. The last reciprocal identity is when we have tangent of theta. Tangent of theta is going to be what? Oh, sorry. I'm sorry. Sorry. I meant to do cotangent. Cotangent of theta is what? 1 over tangent. 1 over tangent of theta. Those are all of the identities. All of the other identities can be derived from these. So these are really the most important ones that you need to know. These are the most important ones you need to know. Yes.
Also call cotangent like cosine over sine.
Cosine, can you call cotangent? So the question is cotangent of theta, is that cosine of theta over sine? And the answer is yes. That is true. That is also one of our quotient identities. Okay, we covered a lot of stuff. If this didn't make sense to you, I would suggest watching some of the videos that I have posted. Because this idea, almost half of the year last year in secondary math 3 was trigonometry, almost half of the year. And there was a lot of important things that you needed to know. A lot of stuff that we covered on that sine is your y value, cosine is your x value. You need to know that. You also need to know your trig identities. These are the main trig identities. And you need to know whether sine or cosine and tangent are positive or negative in what quadrants. Those are important things that you need to know in calculus.